by. All right, so work energy, right? Same equations the same procedure, same equation, same everything as we did for particles. So if you got particles, this should come pretty easy to you, okay? The only thing that we've added is we've added an additional component. Our kinetic energy has energy associated with it rotating as well as energy associated with it translating, okay? Potential energy, right? We just added in a torsional spring. Those things exist as well. And then work being done from state 1 to state 2, we've added a component associated with moments. Moments do work, okay? And so what does that look like? This is what the kinetic energy looks like. We have a translational component and we have a rotational component. And what it looks like in 2G is this. Okay. If we do it around a fixed point, we can get rid of the mvg squared and just use I about the fixed point omega squared. Okay, so that's how the kinetic energy changed. The moment, right? What happened? What it was? We're still going to have linear work as well. Forces times change in distance will do work, and same thing. Very analogous. Work done by a moment is just that moment times change in theta. Okay. And that's if it's constant. I think all of our problems have constant moments, okay? And then we added in a torsional spring. We still have linear springs, which is 1/2 ks squared, and then a torsional spring is 1/2 k theta squared, right? And so we just added in that extra component. That's it, right? Same process we use to solve these things. Free body diagram, just to identify the forces, write energy equation, simplify and expand, kinematics as required, and then solve. All right, and then we were in the middle of this guy right here. This guy's starting out at state 1 over here, and it's rolling over there. And what they want us to find is omega over here at state 2, right? And again, very clear that it's a work energy problem because it's talking about state 1, state 2, and velocities, right? Omegas, as opposed to forces, right? And they give us all the information we need. So we drew a free body diagram of this, right? And we looked to see what's acting on it. Well, we've got that spring force is there, but it's not going to do work because we were going to put it in. It does do work, but we're going to put it in the potential energy term. Mass times gravity, there's no change in height, and we're also going to put that in potential energy. Normal forces never do work, and then the only thing that we had in down here was that friction force, and then we just kind of threw out a thing saying, hey, if there's no sliding, then there is no work being done by that friction force. That friction force is doing something. If it wasn't there, then this wheel would not turn, okay? But it's not sliding, so it's not doing work. It's not pulling energy out of the system, right? And then where it's being accounted for kind of by the kinematics, and the fact that this spring is pulling on it. Like this couldn't make the wheel turn without the spring there either, right? And so it's already the turning part is being accounted for by the spring and our kinematics. So just trust me on that one. It's not doing work. And then don't start looking at how, the moment that this friction force causes, and don't do that, okay? Because it gets too weird. You just trust me that it's accounted for somewhere. Okay. Trust me. Okay. All right. Let's write the energy equation. Next step. Energy. Hey, I write it down every time. The whole thing. T1 plus V1 plus work done 1 to 2 equal to T2 plus V2. Right? I say it just like that in my head. Right? So this thing is starting at rest, so there's no kinetic energy at the beginning, right? Does it have potential energy at the beginning? Yes, right? That spring is going to be stretched, so there is potential energy. Is there work being done from state 1 to state 2? No, we just determined that. There is, but we're putting in the potential energy terms, okay? Kinetic energy afterwards, we're after that, and then potential energy at state 2. Yes. Right, the original unstretched length is 1 foot, and it's 4 feet, that vertical right there. So it will be stretched at state 2 as well. So we've crossed off everything that we can. Okay. 3, expand and simplify. Okay. So we just expand each of these terms. That potential energy at the beginning is just in the spring, ks1 squared, right? That's where all our energy is at. And then 1/2 mvg squared plus 1/2 ig omega squared, right? That is the kinetic energy plus 1/2 ks2 squared. Right? So this here, that's just that's V1. This here is T2. And this here is V2. Just to show you the first time that we're going through it. Okay. So you have to have both of these components, right? That mass center of the disk is translating, right? That mass center is moving. So there's got to be the 1/2 1/2 mvg squared, but it's also turning, which is the 1/2 ig omega squared. You have to have both of those components in it, right? Got to do some kinematics. There's too many unknowns floating around. So we just got to do a little bit of kinematics to relate some things. S's, I'd say S's are down here. S1 is equal to 5 feet minus 1 foot, right? At state 1, this is 5 feet long, right? But the original unstretched length is 1 foot right there. So the stretch is going to be 5 feet minus 1 foot. S2 is equal to 4 foot minus 1 foot. Do you guys ever do little tick marks for feet? Is that a new thing? All right, okay. Jumped right into it. Okay, and then we have to somehow relate VG and omega towards each other, right? So we got S, but then now I still have two unknowns. I have VG and omega, right? And this is the only equation I get. I only get this equation, so I have to relate those two to each other so that I can solve this, right? And so then there's a couple ways to do it. Right? If we just go back to the just general kinematics, we start at a point that we know something about, and then we use this equation. Right? If you have 2 points on the same body, I know the velocity at this point is 0, and I can take a step up to that, and you can, this is the most robust way to do it, is to do it this way. So this is omega in the k direction, and I cross that with 0.75 in the j direction. And what we get is negative 0.75 omega in the I. Right? Or, if we look back at rolling wheel kinematics, right, we determined this once before. Right? Because it's just a rolling wheel. So you might make note of that. I'm okay with you taking that jump as long as it's that VG is equals R times omega. We did this before where we took a step along. And we took a step from one point to another point. But if you don't see it, if you don't see the rolling wheel kinematics, right? If you don't see that it's just the VG and omega related with just negative R times omega, then that's fine. You just go back to this, and you step back, you step through this, and it'll lead you to R times omega. Okay? Either way. If you see it, go for it. If you don't worry about it. Right, last step is solve. Right. So then let's plug in all of our variables into that equation above there. 1/2, our k is 2, our stretch is 4 squared is equal to 1/2 times, again, really careful with your masses, it's 30 pounds, so we got to put it into mass, so you got to divide by gravity. 5 omega squared, so I just substitute in what VG is, right? Just negative 0.75 times omega plus 1/2. Our IG, they gave it to us, 0.335 omega squared plus 1/2 times 2 is our K stiffness, 3 is our stretch. That's it, right? What you're solving for there obviously is omega. Right, to that omega, right? And so just boop, 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 boop. And in my calculator, I get omega is equal to plus or minus 4.04 rads per second. Right. And that's what the answer is, right? But then you can apply a little bit of logic in there and see, is it positive or is it negative, right? Should it be a positive or negative? Positive, right? It'll be roll, right? Just, I mean, energy says, for the energy to be conserved, it'd say it could go either way, right? It could rotate this way or it could rotate that way, and then energy would work out. But it clearly, based off of our kinematics, it's going to be rolling like this. It's going to be rolling with the positive omega. So the answer would be the positive omega. But our math showed us that, and you have to apply a little bit of kinematics. Questions, concerns? See, they're not bad, right? It's the same. It's same thing we've done before. We just have these extra components. In this case, the extra component was simply that IG omega thing, and then a little bit more complicated kinematics. Okay, let's do another one. This son of a bitch. Okay. You got this wheel that's going to be rolling down this ramp. And not only is it rolling, it also has an applied moment as well, right? So it's like a torque to it. And when we talk about moments, it's just something that's coming from external, right? Like an external force or an external moment in this case. That's applied to it, right? Like if you stepped on your gas, that would then turn your axle more, which would cause a torque, which would be kind of what this is. So it's coming from something like that. Okay, and so then it's also starting at one height and it's going down to another height, and give us the radius. They tell us the mass of the disc. They tell us the angle there is 15 down below here. They tell us what the moment is. What is the velocity of the center disc when it's moved to a distance of 0.4? So when this is 0.4, what does it end up doing, right? So this is clearly a work energy problem because it's talking about going from one state to another state. Okay. First step, free body diagram. Got my disc. Got it. Okay. Force is acting on that disc. We got mass times gravity. Okay. I've obviously got that torque, right? And that torque is applied. And I put legs on my M so you can see that it's not the mass there. And then a ramp. A ramp is coming like this. Right, so I'm going to have a normal force acting up like this. Right? And then again, a friction force like this. And again, they're not super important to get these things like really dialed in for the work energy problems. You're just doing it to see what's acting on it, right? Just so we know that we're including the right terms in our energy equation. Okay? So obviously, things that are doing work, gonna do work, we're putting in potential energy. Never does work, never causes motion. Friction force, it's not sliding, so it's not doing work, right? So the only thing in there is that external moment. That external moment will do work. Okay, identified that. All right, step 2. Just cracking open a beer, first thing in the morning. Gotta kill that hangover with the beer. All right, write down the energy case. Say it every time. T1 plus V1 plus work being done 1 to 2 is equal to T2 plus V2. Okay, go through and cross some stuff out. This thing is starting from rest. Mass stationary, this is stationary, so no kinetic energy at the beginning. Okay? Potential energy at the beginning. It depends. Depends on where we set our datums to be. Okay, and we'll get to that in a minute. I'm going to say, I always like to do my datum down at the bottom. So I will say it has potential energy at the beginning because it's going to has a certain height to it. Right? Work being done from state 1 to state 2. Yep, this guy. This guy's doing work. Okay? It's adding energy to the system. Right? Kinetic energy afterwards. Absolutely. Right? That's what we're after. We're after how fast it's going. It's in that kinetic energy term. Potential energy afterwards. Again, depending on how we set up our datums, but I'm setting up my datum so that it's 0 at the bottom. That guy's 0 there. Right? Again, I just like to start with this. And then I know, like, instead of expanding it first, so you could expand it first and then go back and cross stuff out. But I think it's a little bit easier to just take a step first and point it out, then expand. A little less writing. Oh, but I skipped my kinematics. Let's go back to kinematics. Right. Again, you don't have to do them in this order. If I didn't do my kinematics now and I expanded it, we would see that we have... No, I expand next. You're right. God damn it. I think my steps had it this way. It doesn't matter. It doesn't matter what order you do them in, as long as you do them all. Except for I want to keep consistent here. Oh. M, G, Y, 1, right? Plus my moment times my theta. Right? Put my legs on my moment so I know it's different. 1/2 M, V, G squared. Plus 1/2 I, G, omega squared. Right, you need both components. It's going to be translating and it's going to be rotating. Okay? So those are all the things. And again, if you look at it, right, what I need to find in kinematics, I have to define y1, I have to find theta, and I have to relate IG and omega to each other. Right? If I don't do that, I can't solve it. Okay? Kinematics. 4. Kinematics. All right, let's go back up to this. So one thing we haven't done a problem yet in 2D. Oh. We haven't done one in 2D yet. When it taught the MGY, I should make a bigger deal about this. The MGY, it's the change in height of the mass center. That's what matters. It's the change in height of the mass center, not the change of, which is, you got to track something. So in this case, we track the mass center. The mass center goes from here down to here, right? And that's what you have. That's what you have to track, right? So this guy, the hypotenuse here, this hypotenuse is, what is it? 0.4. That's given to us in the problem statement. This angle right here is 15 degrees. That makes y1. This y1. Y1 is equal to 0.4 times sine of 15. 0.1 meters. Okay. So I just got that from the geometry up above there. So a little bit of geometry, a little trig there to figure out what that height is, right? And again, then we'll make y2 equal to 0 down at the bottom. I've kind of said that from the beginning that we were going to do. Okay. Great. We got y1. We got y2. And then we have to figure out what VG is. I'm going to jump right to, this is just a rolling wheel. That's just going to be negative R omega, right? I just noted, like I said before, You could do it the other way. You could do it taking a step from one point to another point, or you can notice that it is a rolling wheel. Wheel, rolling wheel, right? So that's how our V. We just know that's how they relate to each other. We can't put anything else in there. Okay, and then last is have to figure out how far it rolls. Now, I would put this in rolling wheel kinematics as well, right? If you're trying to figure out the circumference of something, right, you do 2 pi times r. Right? That tells you how far you go around. You got the radius, that's 2, and then you multiply it by the angle over which it acts, right? So that same concept applies here when a wheel is rolling, right? Really, it's rolling over its circumference. And so what you do is you take the radians in which it rotates and you multiply it by the radius, and it'll tell you how far it rolled, okay? That's where these things come in. So basically the relationship there, my B would be negative r times theta. Right? Theta be the angle, and we multiply it by the r, and it'll tell you how far it rotates. I keep getting these text messages because my son just got his braces off, and he got his retainer, and he lost it after 2 days. But then the good news is he found it, but when he found it, it had been run over. So, run over. And we knew it. We knew he was going to do it, but what I was surprised with is it only lasted 2 days. And so he has to buy it himself. $110 we just found. $110 to replace it. So my wife is texting, and my son's like, "Oh my God." It's like, well, he shouldn't have lost it. And my other son's like, "Well, I've had mine for 3 years and I've never lost it." I was like, "'Cause you're responsible. Your brother is irresponsible." And I chalk both of those up. That makes sense how you figure out how far a roll, because this will happen on several problems, right? Is how far it's going to roll is going to be the radius of the wheel multiplied by the theta to tell you how far it rolls. So in our case, we're given that 0.4, right? So we could solve for theta. Theta is equal to negative 0.4 all over the radius. And that radius of that guy, to tell us what that is, 0.2. Okay. All right, now we have everything. So now we go back. Last step is solving. Solve. Right, so we just plug in everything we have here. So we got the mass is 5, G is 9.81, height we just determined to be 0.1, plus, oh yeah, so then we gotta work out a few things here, right? So this is whether or not it's a positive or a negative. There's a couple ways to do it. Right, this is the work being done, right? What we did before is if the force is acting in the direction of motion, it does positive, right? If it should be adding to the, right, in this case, that moment, it's gonna be rolling this way, and that moment's applying it to it, so it should cause it to speed up. And if it's speeding it up, then this should be a positive value, right? Because and that's one way to think of it. It's like if the moment's acting in the direction of motion, then it should be a positive value. Or you could do it you could be anal and figure out, well, let's see, keep track of our signs. Our signs are gonna be, that moment is a negative moment, right? And then our theta that we're gonna get is, like I said before, is a negative. You can see down here, right? This is a negative. And so you could keep track of the negative, and then you would get a positive out of it. Or you could just say, well, I know it's gonna be positive because it's acting in the direction of motion. Either way works. We'll do it. We'll put in the signs here. That's the negative 10 is the magnitude of the moment, and that's over negative 0.4 over 0.2. I should be able to do that math, but I'm just going to leave it broken up there. All right, so then obviously the resultant will be a positive. All right, we could say keep track of signs, or know that moments acting in direction of moment or of motion. Right. I'm trying to make that clear there, just how we end up there. All right, and then we got to keep going here. So we got 1/2, the mass is 5, Vg is negative 0.2 omega, that squared, plus 1/2 Ig, we haven't figured out what that is yet, times R, oh, this is 0.2.
Are we trying to find Vg?
Yes.
Why would we change Vg to omega?
Because that's what I did. Well, give me 1 second. Wait a second. Because I was being lazy. Right. That's a good point. I could have. What I should have done. Mark, you were asking the question. Yeah. What I should have done is I could have just flipped this. See what is this? I said Vg is R times omega. I should have said omega was Vg over R, and that could have solved for this. But what I did, I don't know why. I solved for omega, and then I took that omega, and then went back to this, and then got what Vg is. Right. But you're right. Doing it that way would be fine.
You solve for omega in the Ig equation?
Yes. Yeah. Well, let me get Ig. Ig. In this case, this should have been step 0 was determining mass props, but this would be, if you look it up for a disk, is 1/2 mr squared. Like you just calculate what that is. Oh, where did my omega go? Hold on, how was it done yet? This should be back to what you just said. I was like, what's wrong with this? This should be an omega, is what you were saying. Correct. Right. I was just gonna say, what's wrong with this? Right. This would be the 0.2 right here. That R right there is 0.2. That's good. Messed it up. Okay, there we go. That's it for reals. All right, now the only unknown is omega. And so you solve for that omega. And what I got was omega equal to plus or minus 13. And then my Vg is equal to negative R times omega, which is equal to 2.6 meters per second. Right? And it should be negative is what my answer should be. Right, it's really plus or minus, but we know that it's going to be negative 2.6. No, it's not. It's positive. Not the omegas, but just the direction it's moving. Yeah, because it's going to be moving to the right. Cool. These aren't bad, right? Not bad. Almost. A little fun even. A little fun. A little fun? Good time, Jermaine? Nothing else you'd rather be doing at 8:30 in the morning on a Monday? Look at this son of a bitch. All right? This is the grand finale right here. If you thought that was fun, let's do this one. Right? This one's a good time. This one we got 3 bodies. Right? We got 3 bodies floating around. And we got some real kinematics. I know you've been missing those kinematics. Here's some real kinematics for you, right? We got to figure out, right? You can imagine. So this thing's going from this state down to this state down here. It's going down to here. Right. my God, I can't, I really, it's embarrassing when I can't draw a circle with the help of drawing a circle. There we go. So yeah, so it's going from the state up there and it's going down to the state right here. So you can see we're gonna have some serious kinematics going on. We have to relate how this thing moving this way affects what this is doing and affects what this is doing and all sorts of stuff. But, and you're like, oh my God, this is gonna be really hard. It's not easy, but it also isn't that hard because we're just gonna stick to the process. If you follow the process, it leads you right to it, okay? Free body diagram, we gotta do a free body diagram of this thing, okay? You could draw those free body diagrams at any state, right? At any state, those free body diagrams apply, right? But we have to do one per body, right? So we're gonna do one per body. One, F, B, D, right? Then we're gonna do one for the block over here. Right, so we've got acting on there. You got mass times gravity pulling down. Oh, but then we got so many masses floating around, you gotta be careful about calling them out. This is mass A times gravity. Do we label any of these things? Let's call this guy A. What do I do for the other guy? Do I call it bar? I call this bar. Okay, and then over here, oh, they got B. This B over here. Okay, so also you'd have some sort of normal force acting on it, right? You'd be pulling or pushing, probably pushing to the left, doesn't matter, but there would be some normal force. There would be something keeping it in this track, right? So there'd be some sort of normal force pushing on it.
Why is there not two normal forces?
Or like one on the other side too?
Yeah.
You could. I mean, it will only push one way, right? Because it's pulling. But you could write it either way. You're right. Well, I'll do it for you. For you. What is your name again? Walter. I just learned a new name today, Walter. You're kind of a pain in the ass, Walter, but I'll just go ahead and I'll learn your name. I should have learned it a long time ago, Walter.
Well, I mean, if we're gonna
Do it right. But technically right, you wouldn't have two. Yeah, but it will only react on one of them.
Well, let's just do it.
Right? Does that make sense, right? Because it's either pushing or it's pushing, but it's not pushing, right? For both, with the exception of if it was pre-stressed of some sort, right? If the wall kind of squished it from both sides at the same time, then. Right? We don't know. We don't know. It's all theoretical. We're in a pretend world, so we'll put it in normal. We'll call this one Walter's the horrible force. Walter's N. If you get it, Walter's at normal force there. Right, but you're right. It could come either direction, so you're right. So that's that. And then the other thing acting on it would be this bar would be pushing on it, right? Beep. This would be F bar. We'll call F bar 1. It would be pushing on it, right? It would be there, right? It would be reacting in some capacity. This bar coming in would definitely be pushing on that in some capacity. Okay? And again, not super important to get any angles. You could draw it at any state. We're just looking to see what's doing work, right? And we're actually gonna come up with a little thing here. And then we're gonna have the bar. Oh, I wanna make that black. And it gets a little steeper here. Black guy, there we go. And then so what we got acting on that bar? Well, we have F bar, and I'm doing this on purpose. I'm putting it off at some angle. It doesn't really matter. It's not a statics problem, and things are moving. It's not going to necessarily line up perfectly with that bar. With statics, it lines up perfectly with that bar. In this case, it's unclear because things are moving around. It's hard to tell. So I purposely just put it at some random angle. And then the other side, that's F bar 1. On the other side, we're going to have another one. This is F bar 2. Okay. And then we're also going to have mass times gravity acting on this thing as well. And this is B M bar times G. Okay? And they don't have, F bar 1 and F bar 2 do not have to be equal to each other, and they will not be equal to each other because things are moving. Okay? So that's why we call one F bar 1 and the other one F bar 2. Right? And then we go back, last thing is the disk B. The help of my thing here, see if I can draw a circle. Nailed it. Okay, things acting on that disk. That's just a little big. I did it though. All right, force is acting on this. Now we got a normal force acting up, friction force to the left, mass times gravity going down, mb times g, and this will be F bar 2. Okay, that should be everything acting on there. This roll. Yes. Yeah, we do. The center bar is a pitch. We'll do it. Yeah. You son of a bitch. Oh, I don't want to do it right now. I don't want to do it right now, Walter.
Well,
No, I'm looking to see where I do it eventually. Oh yeah, I do it way down there. Way on the next page. I'm gonna leave you in suspense. But yeah, you'll see you have to get it later. I get a little loose with it. What I don't want to lose is this right here. I don't want to lose this momentum that we have right here, right? So when we look at what we're doing, these free body diagrams are for, is to figure out what's doing work, right? Normal force, does it do work? Walter's normal, maybe, but usually it won't, right? So normal force isn't going to do work. Mass times gravity, it does work, but we're going to put in potential energy. F bar, that's external to this, right? That's external to this. And so that could be doing work, right? But then here it is over here as well, right? It's reacting on the other side. There's F bar over there. And just what we did once before, right? When we did this for particles, right? This one is acting this way, and then it's going to be moving down, and the other one is going that way, and it's going in the direction of motion, so they cancel each other out. They move the same, right? This guy is equal and opposite to this guy. This guy goes down, this guy goes in the direction of motion, right? So this one would do negative work, this one would do positive work. They cancel each other out. And this was one of the things we discovered once before for particles, was that if it's an internal force to the system, then it doesn't do work, right? And so this guy and this guy will not do work, neither will this guy and this guy. Technically, they do work. This one does work, all right, this guy pushing back does work on this bar. This guy acting on the bar does work, this guy acting on this does work on that disk, but together they cancel each other out. It's the same amount of work. They're equal to each other, right? Equal and opposite, so they cancel each other out. So that's a big postulate, if you will, that I wanted to point out. And I think the book goes through a full derivation of this, but I think you guys, most of you guys, do not do work, right? Equal and opposite acting over the same distances. F bars don't do work. Right. Makes sense to everybody, right? Kind of equal and opposite. So they're internal to the system. They don't do work. They do, but they kind of cancel each other out. It's all encompassed by the whole thing. Okay? Energy equation. Or sorry, yeah, write down the energy equation. 2. Just so we know, kind of simplify this down to what we need to know. All right. T1 plus V1 plus work being done 1 to 2 equal to T2 plus V2. Right? Starting out at rest. No kinetic energy. Potential energy. Sure. Again, I like to define my datums being 0 down at the bottom. Right? And it's going to be really clear that there's a bottom. In this state right here, that's the bottom. Right? So we're going to define it that way. So we're going to have potential energy at the beginning. Work being done from state 1 to state 2. Right? That is, we just determined there's going to be 0 work being done from state to 2 because there is no external force or external moment acting on the system. Nothing, no energy being added to the system. Right? And then potential energy, like I said, I'm going to set it up so that my potential energy is 0 down at the bottom. Okay, so that's it, right? It's going potential energy into kinetic energy. You're like, oh man, that's not so bad. Well, son of a bitch, look at all those things we have to keep track of, right? So let's write out this thing. You got 4 minutes. We got plenty of time. So let's expand. Next step is expand. Expand. All right. So it's potential energy at the beginning. It's just mass times gravity times height. So we got MA times G times YA1, right? Because the height you're going to have a different height for every object that we have. So we have to put a little subscript on there. Plus M bar times G times Y bar 1. Right? And then the disk doesn't change height, right? It stays the same height. So we don't have anything for the disk. Right? That's it on the left-hand side. The right-hand side of the equation, we need everything. We have 1/2 MA VA squared. Okay. What's nice is that's all we're going to have for this bar, or for this A, right? The A is not going to rotate, right? It's not rotating. It's stuck in there, being pushed on from both sides at the same time, and then, which is impossible. But then it's coming down. It's sliding down, but it's not rotating. But you're right. If it did try rotating, that other guy would kick in and keep it from going. That's right. That's,
Normal resist motion.
yeah, that's right. That's right. That's normal resist motion, right? So then you got 1/2 MAVA squared. So there's no translation component. There's no rotation component. But C, or bar, I guess I've been calling it bar this time, this is going to have both components, right? Because it is translating and it is rotating, right? It's going to rotate as it drops. So this one, we have to have both of those. 1/2 M bar V bar squared plus 1/2 I bar omega bar, right, squared. Son of a bitch. Look at it. I'm running out of room. I'm going to go. Okay, that's all. So this is all. This is TA. Right? This is T bar. Right? And so we still have the disk to go. The disk is going to be plus 1/2 MB VB squared plus 1/2 IB omega squared. omega B. That guy is TB. Right? Because again, that disk is going to be translating and rotating, so it has both of those. Okay? This guy doesn't rotate, so then it only picks up that. Okay? Right? Well, son of a bitch. Right? So what are the unknowns in this? Right? Well, I need to determine what YA1 is. I need to find what Y bar 1 is. That's fine. That's just going to be geometry. But then I have to relate, right? I got VA, V bar, omega bar, VB, and omega B, right? Way too many unknowns. I need one. I get one unknown. So I got to relate all of those things to each other. That's where kinematics come in. And unfortunately, those kinematics involve your favorite part of going, take a step from here to here, take a step from here to here, and then constraining this one in the vertical direction, right? And so we're gonna have to do that. So that's where we'll take off next time, okay? Is we'll do that. Right, and then also note, this is in state 2, right? These kinematics is in state 2, so we do it when it looks like this, right? Down at the bottom. Cool beats? Break.